Hello, everyone. Thanks for tuning in. My name's Thomas Yazinchuk, a fourth year computer science student at University of Victoria. Today, I'm excited to share the research that I'll be presenting um, that was presented at ARES 2024. Uh, the talk's titled Sybil Attack Strikes Again, Denying Content Access in IPFS with Single Computer. Over the next 10 minutes, I'll walk you through three things. Number one, how single low resource machine can launch a Sybil attack powerful enough to censor files on IPFS. Number two, the experiments that prove it works in practice. And number three, the most importantly, a set of lightweight defenses that the IPFS community can adopt right now. Whether you're just building decentralized storage, research peer-to-peer security, or just curious about Web3 and these findings matter for every project that relies on a distributed hash table. So let's dive in and get into the nitty-gritty of the paper. To understand why this attack matters, let's zoom out for a moment. First, the promise of decentralized storage systems like IPFS is censorship resistant. There is no single server to shut down, no central authority to lean on. Second, that very openness invites adversarial threats. In peer-to-peer networks, the most notorious is the Sybil attack, one bad actor spinning up many fake identities to gain outsized influence. Now let's look right side of the diagram. That is, a single laptop represents an attacker who's generated 20 or 200 Sybil peers. Because IPFS's lookup algorithm simply asks the closest peers for information, our attacker can sit at the crossroads and catch every request for a targeted file and quietly drop it. Our research shows that only one computer, about 90 minutes of key generation, and 0 special privileges are enough to block content network-wide. IPFS currently has no built-in check that says, wait, why are all these different peers coming from the same place? In other words, the very system designed to dodge central control can be re-centralized by a single determined adversary. That's why Sybil resistance isn't just a side quest, it's mission critical. With that motivation in mind, let's unpack how IPFS works under the hood so we can see exactly where the exploit slips in. To understand the attack, we first need to understand how IPFS works at its core. IPFS stands for Interplanetary File System. And while the name is a little ambiguous, the goal is clear: to create a fully decentralized system where content can be shared globally without relying on centralized servers. Instead of URLs or IP addresses, IPFS identifies files using something called a CID, or a content identifier. Think of it as like a cryptographic fingerprint. It's generated by hashing the content itself. If the file changes, so does the CID. Now, here's where discovery comes in. Whenever a peer wants to share a file, it publishes a provider record, essentially saying, I have this file, into a distributed hash table or database called a DHT, which is a distributed hash table. Specifically, IPFS uses a variant of the Camellia DHT, where peers are organized and discovered based on XOR distance between node IDs and content hashes. So if I want to find a file with CID 123, I query DHT, which routes my request closer and closer to peers that are nearby in ID space. This lookup mechanism is elegant, but as you'll soon see, it's also where Sybil vulnerability creeps in. Let's break down how routing works and how an attacker can manipulate it. Now that we've seen how IPFS finds content through the distributed hash table, or DHT, let's talk about what makes it vulnerable: the Sybil attack. A Sybil attack is when a single entity, for example one laptop or server, generates many fake identities in a peer-to-peer network. These fake nodes are indistinguishable from real ones unless a system has safeguards in place. The result: attacker gains disproportionate control over the network. They can intercept messages, redirect traffic, and in the case of IPFS, prevent content from being found at all. So why is this so dangerous in IPFS? Because when a file is published, the DHT stores its provider record on the 20 peers closest to the file's CID. If an attacker controls those 20 slots, or even most of them, they can capture or drop any attempt to retrieve the file. And here's the catch. It doesn't take a supercomputer. One machine running 20 processes carefully chosen peer IDs is enough to eclipse legitimate providers. If it helps, think of it like a phone book full of fake listings. If you're trying to call to someone, but every number you dial goes to the same malicious operator, that's the power of Sybil attack in a system that doesn't verify who it's talking to. And we'll see next, IPFS Offender offers attackers the perfect opportunity to exploit this setup. To understand how the Sybil attack actually hijacks IPFS, we need to take a quick look at under the hood on how the Camilla distributed hash table, or DHT, works. Camilla organizes all peers in a virtual ID space. Think of it like a big circle of node IDs, where peers want to find a piece of content. It looks up the content's ID, which is just a cryptographic hash. Here's where the clever part. Instead of searching randomly, Camilla uses the XOR metric distance. It XORs the requesting node's ID with the CID hash and picks the peers that are numerically closest in that space. Every node keeps a routing table made up of what are called K buckets. In IPFS, K equals 20. These buckets help the node iteratively query closer and closer peers with each hop until it finds the 20 closest ones to the CID, or content identifier. Think of it like a treasure map. With each clue, you get closer to the target. The DHT helps route you towards the treasure, that is, if the file you're looking for, by narrowing the search at every step. But here's the catch. Camilla trusts that the peers it finds are honest. If the 20 closest nodes are actually Sybils, you're following a fake map, and the treasure is never going to show up. That's exactly what the attacker in our study exploits. And next, we'll look at how they do it, step by step. Now that we understand how IPFS uses Camilla to route lookups based on XOR distance, here's how the Sybil attack plays out in this context. A Sybil attack is when an adversary creates many fake identities. In this case, fake IPS peers. From the outside, each Sybil looks like a legitimate node, but behind the scenes, they're all controlled by the same operator. The trick is to generate peer IDs that hash very close to specific CIDs, the ones the attacker wants to suppress. Since the DHT lookup always targets the 20 peers closest to the CID in the XOR space, the attacker just has to pre-compute a tight cluster of nodes that are around it, being fake nodes. Once those Sybil nodes dominate the lookup space, two things happen. One, when the content is published, the provider record is stored only on the attacker Sybils. And number two, when someone tries to find the file later, their query is intercepted and goes nowhere because the Sybils refuse to respond with the real info. So with just 20 well-placed fake peers, the attacker can eclipse the real ones. Think of it like trying to find someone in a phone book, but every page has been replaced with fake entries, so you keep calling and the line never connects. Next, I'll walk you through exactly how the attackers generate those fake peer IDs and sets up their Sybils and executes the attack with surprising ease. Here's how the Sybil attack actually unfolds, step by step. And what's most striking is how simple and low cost it is to execute. Step 1 is pre-computation. Since peer IDs and IPFS derive from public keys, the attacker brute forces key pairs until the resulting peer IDs fall close to the CID in XOR space. On a normal desktop CPU, generating 20 well-positioned ID takes around 90 minutes, which really isn't that long. Step 2, those 20 Sybils are spun up, each in its own process, but they all come from the same machine, often even the same IP address. Despite that, IPFS's lookup mechanism doesn't enforce any IP diversity checks during lookups. Step 3, once a local peer tries to publish a file, it performs a DHT put, sending the provider a record to the 20 closest peers. If those are all Sybils, the attacker now controls who knows about that file. Step 4, when a user tries to fetch this file, their lookup is routed back to the Sybils, which either drop the request or respond with nothing useful. The content is effectively invisible, even when it's still online. The end result? Real data becomes unreachable, and the user gives up. It's like showing up at a help desk where 20 people are ahead of you in line, but they're all fakes, and none of them move, none of them help, and you never get through. And remember, this entire attack is performed using a lightly modified open source IPFS mode. Nothing exotic, nothing expensive. Now let's look how well this attack worked out in practice. After designing the attack, they put it to the test in a controlled experiment using only their own test content, so no real data was affected. They deployed 20 or more Sybil nodes using the standard IPFS Kubo client with a minimal tweaks and tested an attack on both Kubo 19.2 and 20. The results were clear. In both versions, the attack succeeded in over 90% of cases. That means the attacker was able to catch all or nearly all provider records and make them effectively unreachable. Even more concerning, it was done from a single machine on a single IP address. There was no need for botnet or fleas of VSPs. IPFS didn't stop or even slow it down. It didn't take long either. After 90 minutes of pre-computing PRIDs, the Sybils were live and effectively finished in under 15 minutes. From the end user's perspective, that's all it takes. If the file doesn't show up after a few minutes, most users give up. So even if the content is technically still exists in the network, it's been functionally censored. To put plainly, all roads lead to the attacker's nodes, and there's no alternate route to find the content. Next, we'll talk about what these results mean and how it compares to the previous DHT-based Sybil attacks. So what does this all mean in a broader context? Let's talk about what it makes this attack powerful and where the limits are. First, the strengths of the attacker is shockingly low cost. It requires no botnet, no GPU cluster, just a single desktop and about 90 minutes of key generation, and a slightly modified IPFS client. It's also reproducible. They tested across multiple versions of the Kubo client, and the results were consistent. But it also is important to know what the attack is not. This isn't about hijacking data or corrupting the network, it's a targeted denial of access, blocking lookups by dominating the DHT neighborhood around a specific CID. It also assumes a relatively stable network during the attack window. If the DHT churned faster or aggressively refreshed entries, it might affect the results. But in the test in the paper, the attack was still highly effective. When they compare the study to prior Sybil attacks in networks like CAD or Ethereum's DHT, the techniques are similar, but one is easier and cheaper to pull off. Older attacks often require 100 plus Sybils or simple IPs. Theirs worked with 20 Sybils and a single IP. The good news is we don't need to redesign IPFS from scratch. To defend against this attack, a few smart changes at the lookup layer could be made Sybil denial attacks much harder to pull off. First, the IP diversity enforcement. This means limiting each DHT lookup to one peer per subnet, like in 24 IPv4 or 56 in IPv6. That way, a single IP address can't pose 20 different neighbors. It's simple, fast to implement, and would have stopped our attacker outright. Second, we can introduce disjoint paths, a concept borrowed from S/Camilla. Instead of doing one lookup, nodes could run multiple lookups in parallel, each along separate paths. Even if one route is Sybil poisoned, the others still have a chance to reach honest peers. IPFS is aware of this idea but hasn't implemented it yet. Third, there's statistical anomaly detection. PRIDs supposed to uniformly distributed. If a bunch of them clusters tightly around a CID, that's suspicious. We could flag it, filter it, or at least degrade it. And finally, for longer-term hardening, we could explore proof-of-work requirements, write smarter walk stock strategies, or storing fallback replicas with peers beyond the top 20. These come with more complexity, but they raise the cost for any attacker. With defenses like these, we could drastically reduce the attack surface without sacrificing IPFS's openness. To wrap up, here are the key takeaways. First, this attack is simple but incredibly effective. Just 20 symbols all running from a single machine can block access to content across the IPFS network. No botnet, no statistical tooling. Second, there is no single fix. Defense in depth is the answer. We need basic IP diversity checks, disjoint lookup paths, and anomaly detection, and possibly longer-term upgrades like proof of work or fallback replicas. Third, This isn't just about IPFS. Any system that relies on DHT, especially in the Web3 ecosystem, needs to treat Sybil resilience as a non-negotiable design goal. This work shows even open, decentralized networks can be re-centralized by one attacker with one laptop unless we build outright guardrails. So here's a call to action. You should read the paper, contribute to the conversation, and if you're working on IPFS or any DHT-based protocol, join the push to implement these defenses. Thanks for listening. I'm happy to answer any questions down below. I hope you enjoyed the video about the paper and any defense or strategies I proposed. If you have any modifications or suggestions, please leave them down in the comments. Thank you very much.